There we go. So, first question for you. Start. What bonds two atoms together? Is it their inner electrons, their valence electrons, the octet rule, both A and C, or both B and C? What is it that bonds two atoms together? A couple more seconds. Get your answers in.
What page did you say, Ron?
5 is the one that you will need. At least it's 5 in my packet, so it should be in yours too. Okay, I'm going to end this anyways, and we should say B, valence electrons. Valence electrons, that's what's actually doing the bonding. Some of you were thinking that, well, the octet rule, that doesn't actually bond them together. It helps guide us somewhat, but it's not actually involved in the bonding. Common misconception. So we have 3 types of bonds. We have ionic, we have what is sometimes called pure covalent, or just covalent, and polar covalent. We've talked about ionic at length. We're going to talk about ionic at length again today, and then we're going to get into our 2 different types of covalent. Again, sometimes the one that just says covalent is called pure covalent. P-U-R-E, pure covalent. So, looking at ionic bonds, we know that they are going to have atoms that exchange electrons, and then those will form ions. And they exchange so that they may be in the same isoelectronic series as the nearest noble gas. And again, we looked at isoelectronic series. That just means that they have the same electron configuration as the nearest noble gas. So their protons are still what their protons normally are, otherwise we would be changing the atom, but we're just changing the electrons. Okay, here's another question for you. When we're talking about anions, what type of charge will it have, positive or negative? And is that because it gains or loses electrons? And would it be a metal or a non-metal that we're talking about? Put 20 seconds on the clock. Let's get those answers in. We're missing someone still, but C is the correct answer. So, an anion, a negative ion, that's the way that we remember that one, a negative ion, is an ion that has a negative charge because it gains electrons, and the ones that gain electrons are nonmetals. Okay. So, I want you to write the electron configuration for each of these, and then write down which noble gas it would be like when it forms an ion. Oops. What I want you to do in your clicker, once you've written everything out, is write the symbol for the noble gas that it would be in the same isoelectronic series for. We'll do magnesium first. So just the symbol for the noble gas, so either HenearKrXERN, that magnesium would be in the same isoelectronic series as. Nope, I want you to type in the symbol, either HenearKrXE or RN. Yeah. Really?
Just on the one.
Okay, do what you can then.
Do no, go to the 2. The 2 is the one that has the A.
Excellent. Thank you. Your electron configuration, if you wrote it out, should look like that, and it would lose these 2 electrons, oops, lose those 2 from the 3rd energy level to give us an electron configuration of 1s2, 2s2, 2p6, which is the same isoelectronic series as neon. Let's see. Good, we got a lot of NEs. Okay, next one then, same thing. For fluorine though, for fluorine, once you've written the electron configuration, you can figure out which noble gas it would be in the same isoelectronic series as. Put 20 seconds on the clock. Let's get those answers in. Okay, so the electron configuration for fluorine is 1s2, 2s2, 2p5. That is just 1 away from being the same as neon. Good. Got more neons this time. Excellent. So what it would do is get an electron from somewhere so that it could be full. So we've got 1 electron coming in, and that would give us the same isoelectronic series as neon, 1s2, 2s2, 2p6. What questions do you have so far? Glad it seems for a lot of you it's review. That's good. Katie.
This has some others, but so gaining and losing electrons, it doesn't completely change what element it is. It's usually because of protons, so how can we say like fluoride is 1 away from being neon even though there's different protons?
In the same isoelectronic series. So we're not saying that it's the same as neon, but it's going to behave as neon would chemically. Good question. Okay.
Can you just round here something?
Whichever one's closest. Yep.
What happens if there's even space?
So if we're carbon, silicon, germanium, or tin or lead, they could go either direction. We need more information. Most of them are going to act as nonmetals, and we're going to get to that very, very soon by looking at this chart on page 5. Good, we're thinking ahead. So, an ionic bond is going to form between elements that have very different tendencies to lose electrons. So here's another question for you. What is it called, and what two types of elements are likely to bond ionically? So when we're talking about different tendencies, is that electronegativity, isoelectronic, electronegativity, or isoelectronic, and is it metals and nonmetals, or nonmetals and nonmetals? And if you're on that page 5, that should help you figure out your answer to this one. Put 20 seconds on the clock. Again, page 5 of the data packet to be more clear. Okay, that does look different. Let's see. So some of you, it's on page 8. Thank you. Okay, so we are looking at electronegativity. That is absolutely correct. And a metal and a nonmetal. So all of you that got A, got it 100% correct. So ionic bonds, metal and a nonmetal, most often. And it's due to the electronegativity differences, which you learned in the last unit means its ability to pull electrons towards itself in sharing bonds.
So how do so metals can bond with each other, and metals can bond with metals, right?
Yes, and we're going to talk about that in section 4.4 after break. Okay, so electronegativity is the ability of an atom in a molecule to attract electrons to itself. The higher the electronegativity it has, the stronger the pull it has. So if we're looking at page 8 or page 5, depending on what your packet is printed at, where it's showing the electronegativity values at the bottom is the element and then electronegativity values. We can see that the one that has the highest electronegativity is fluorine, which makes sense because it is so close to being complete and it's so small that it really wants to pull electrons towards itself. Yeah.
The electronegativity have anything to do with maggots?
Not completely. We can kind of think about them in the same manner, but not really. Good question. Okay, so here's a chart that kind of illustrates this, but again, your actual values are better in here. You'll want to use these. So fluorine here in this image is 4.1. It's better to use 4.0 like it says in your data booklet. Francium, it says it's 0.9. Really, we would use 0.7 like it is in our data booklet. We can see we've got a nice trend. We're increasing as we go to fluorine, we're decreasing as we go to francium because fluorine really wants that electron. Francium's happy to give it away. Yeah.
It kind of seems like there's almost like a hump like in the middle where the metals are.
Yeah, the transition metals get a little funky for us because the D energy level isn't as nice and clear cut as the S and the P. So there is some variability in the middle there. And they don't differ all that much, but yeah, good observation. Yeah.
So because of the hump, is there anything that breaks the trend, or is it all?
Well, sort of.
Yeah.
Is there any elements that aren't consistent with the trend?
Just where that bump is, and again, it's just going to be those transition metals.
Why
Good
is
question.
transition metals so funky and like everything is different?
Because their D energy level is where their electrons are, and those do not go out as the furthest ones. There's a 4s and then the 3D, and they overlap, and so they can lose different amounts. Mm-hmm.
Why are period 1 and 2 mostly blue when those are also very reactive?
Because they're reactive in the other way. So they are going to easily lose electrons as opposed to easily gain them.
So could you also say that a lower electronegativity would prove how often you are, or how likely you are to
To
lose?
react? Yep.
Okay.
Yep.
So electronegativity isn't necessarily a measurement of how reactive an element is. It's more of
It's a measure of how much it's going to attract electrons towards itself. Yep. Katie.
So like, why is He? Because I see the top one is.
Yeah, so the noble gases are not on here because they don't pull electrons towards themselves because they're not going to form bonds. And hydrogen's always an oddball. Okay. So, when we're talking, I'm going to do a little bit of math with you here for a second. When we're talking about the difference between things, are we talking about addition, subtraction, multiplication, or division? Put 20 seconds on the clock. It just A, B, C, or D, right here. 10 seconds. We're talking about differences, electronegativity differences. Good, the majority of you got it. Differences, we're talking about subtraction. So we're going to take the values that we have on this chart and we are going to do some subtraction to figure out whether the things that we have are going to be pure covalent, which has zero difference in the electronegativities. So when I'm looking at a bond between two different elements, we're looking for 0 for pure covalent. Ionic is when we have 1.8 difference or greater. Polar covalent is anywhere in between. So anywhere between 0 and 1.8. And you will want to memorize those numbers. Okay, let's look at our chart. Manganese, Mn, and nitrogen, N. Manganese and nitrogen. So we see nitrogen. Again, some of you are page 8, some of you are page 5. If you don't have the data booklet, you can take a look at the chart that was printed off in your notes, and those have some of the values as well. So nitrogen is at a 3, and manganese is at a 1.6.
What does the chart look
Looks like this. It says first ionization energy, electron affinity, and electronegativity of the elements. It's in
like? Oh, the
data booklet. Yep.
why Mn is 1.5?
Ay, ay, ay. Okay, use 1.5 then. That'll actually be easier. So, I need you to type in, is it A, pure covalent, B, polar covalent, or C, ionic?
Wait, are we manganese or nitrogen?
Manganese subtracted from nitrogen. A for pure, B for polar, C for ionic. So 20 seconds on the clock. Oops. We're all in. And the majority of you are saying polar covalent by doing the math. That is absolutely correct. So normally our old rule of thumb, metal and a non-metal, that's ionic. But that was before we knew about polar covalent. If we look at the electronegativity, they're actually going to somewhat share their electrons, their valence electrons, because neither one of them has enough pull to pull those electrons completely from the other one. Duncan?
Did you say there were specific numbers for each of the different ones?
Yes. Yep. Okay, here's another one. Oops. 2. Oxygen and aluminum. Oxygen and aluminum. Find them on your chart. I've got for oxygen 3.4 and aluminum 1.6. Is that what you guys have? 3.5 and 1.5? Okay. Use those then. 20 seconds on the clock.
What happened? I know it probably doesn't seem possible. If we went to negative,
Then do the absolute value. Make it positive. Yep. Couple more seconds. Okay, we should have a lot of ionics because the difference is 2. 2 is greater than 1.8, therefore it is an ionic bond. The oxygen has enough pull to pull those electrons from the aluminum. Okay, so we have oppositely charged ions attracting. Those are electrostatic forces. And a bond forms an electrically neutral compound. It is not normally 2 atoms bonding in isolation. Generally, when we're dealing with ionic compounds, we're going to have a lot of each of the atoms involved in what forms a 3D ionic lattice, which is a crystalline structure. The crystals are going to have a fixed arrangement of repeating units. So if we have table salt NaCl, which you know forms nice little crystals, it's an Na and a Cl and an Na and a Cl in a 3D structure. And that's why we get those crystals that we get. Sodium cations attract the chlorine anions. That's what holds them together. The symbol that we write, however, is going to be the smallest ratio of those ions present. So we write NaCl rather than Na1000, Cl1000. Actually count out how many of the atoms we have. Okay, covalent bonds, both pure, or only looking at pure right now, when we have 2 or more atoms that equally share their valence electrons. It's going to be between nonmetals that have the same electronegativity value. This is not metallic bonding, so we're not going to be dealing with metals at all here. Oops. Can you think of any molecules that we've talked about quite a bit that would be a pure covalent bond? What?
Water.
Nope, because hydrogen and oxygen are different, 2.2 and 3.4. No, because that would be a nice ionic one. That's quite a bit of a difference. That's a 3.0 is a difference. No? We've talked about them quite a bit. Some nice obvious ones. I still didn't catch that. Nope, that would be a nice ionic bond. 2 atoms that equally share electrons because they have the same electronegativity value. What about something you're breathing right now? oxygen and oxygen, absolutely. So all of the diatomics that we've been talking about so much, those are all pure covalent bonds because they have the same electronegativity value. Good. Okay, polar covalent. We have two or more atoms that are unequally sharing valence electrons. There's going to be a small difference between the electronegativity values, greater than 0 but less than the 1.8. And sometimes these do involve metals and nonmetals. They often create what is called a dipole, which is a center with a positive charge and a negative charge. So one of them pulls the electrons towards it more, so it becomes more negative. The one that has the electrons pulled from it more often becomes slightly positive, but not enough to be a full charge. So, some reminders about writing the ionic compound symbol. So the easiest way for us to do it is to look at the charges and crisscross. We could look at the valence electrons. For example, if we have element X with 2 valence electrons and element Z with 7 valence electrons, that would show what the transfer would be. The board is not behaving. So what this is saying is I could draw out some element X, which doesn't exist, it's just made up, with 2 valence electrons. I use dots to represent valence electrons. And my Z has 7 valence electrons. When I draw out in this form, I do at maximum 2 per side, which is helpful to see because you know you need 8 total for it to be nice and stable. So I would have 1, 2, 3, 4, 5, 6, 7, 8 for it to be stable. So how many more does the Z need? 1. X can give that 1 over. What was that? Because it's there. Okay. The Z, though, or the X is not stable yet. It's got to give up 1 more, so we could add another Z to it. 1, 2, 3, 4, 5, 6, 7. Give that 1 up. So now my symbol would be XZ2. So a way to draw it out. Yep.
Is it possible to have more than 8 valence electrons?
No. No. Good question. Yep.
Or if X is helium and it doesn't have the
What was that?
X is helium and it doesn't have the electrons.
Helium does have 2 valence electrons.
But
But
then it gave up both of them.
yeah, we're assuming that this is a metal. You're right. It could be helium, but that would be crazy to use that as an example. Okay. Okay, so we need to remember that when we're naming, we need to ask ourselves, is there metal? If yes, there is, we ask ourselves if there's a transition metal. If there is not, then we have our type 1 ionic bonding. We list the metal first and then the nonmetal with IDE. So NaCl is sodium chloride, CaBr2, calcium bromide.
What's the longest named compound?
That's a good question. It's going to depend on whether we're using the systematic naming or the common naming of things. And then we'd be dealing with organic molecules that would be much larger. Okay, if we have polyatomics, we list the metal first, but we do not add an IDE to the polyatomic anion name. Or we list the polyatomic cation first and then the nonmetal anion with an IDE at the end. So Ca3PO42 would be calcium phosphate, and NH4Cl would be ammonium chloride. If you're still struggling with naming or writing symbols, please watch the videos on YouTube.
I subscribe on YouTube.
Excellent, thank you. Got quite a few subscriptions now. Okay. So this time we ask ourselves, is there metal? Yes, there is, but this time our metal is a transition metal. So it's the same as before, except we need to use Roman numerals to indicate the transition metal's charge. So remember, you should know these Roman numerals. Okay. When we're writing the symbol, we crisscross the charges of the ionic compound. So if we have iron 4 chloride, iron is a 4 plus, chlorine is a 1 negative because of where it is on the periodic table. We crisscross those, we get FeCl4. Copper 2 oxide, copper is a 2 plus, O is a 2 negative. I crisscross, I get Cu2O2, but that's not right. Should be CuO. Lowest common factor when we're dealing with ionics, CuO. Okay, if we are writing the name, we can reverse crisscross. Write very quickly because this is all review. And we have to move on so we can get enough time to do other stuff at the end. Write very quickly.
This was one packet, so they were all like
That's because it's all review. Okay. So, if we're writing the name, we reverse crisscross to find the original charge of the cation if we are dealing with a transition metal. So, ZnCl2, I reverse crisscross. I get Zn2 plus Cl 1 negative, zinc 2 chloride. If I have FeO, I reverse crisscross. It looks like it's Fe1 plus O1 negative. However, oxygen is always a 2 negative because of where it is on the periodic table, not a 1 negative. So, it's iron 2 plus O2 negative. Iron 2 oxide.
Why does the iron go to 2 if the oxygen is
Because they had canceled out here, and if oxygen is a 2, that means that the iron had to have been a 2 as well. Uh-oh.
Wait, why is the iron?
Because it had to have canceled out with the oxygen, and oxygen is always a 2. Always, always. Okay, here we go. It is going crazy. Okay. You will be turning in your clickers in a second here. When you do turn in your clickers, we are going to be grabbing your homework worksheet. Worksheet 1 is due tomorrow. And then hopefully we'll have some time for some birthdays and half birthdays and past birthdays and early birthdays.